Welcome to the Physics Lecture Hall. This is where we put the physical laws governing our universe to the test. Look at this classic demonstration. A student on a frictionless swivel chair with arms fully extended rotates at a constant, relaxed pace. But watch what happens next. The student pulls their arms tight against their chest, and their rotational speed instantly multiplies, turning them into a blur. Notice what is missing from this sequence. Nobody gave the chair an extra push. There is no hidden motor under the seat. No external force was applied to the system to cause that sudden acceleration. This effect is visible far outside the laboratory. Look at these trapeze artists suspended midair. They rely on the exact same physical mechanic. By manipulating their body shape in free fall, they completely control the speed of their flips. The rotational speed of a spinning object relies on exactly how its mass is distributed through space. To understand why this happens, we need to define torque. Torque is an external twisting force that changes how something spins. Think of a hand pushing a bicycle wheel, or the friction grinding inside a metal bearing. When you remove all of those external twisting forces, you create a torque vacuum. In this state, the system's total angular momentum becomes a constant of motion. It cannot be created or destroyed. This formula is the rotational version of Newton's second law. The equation tells us that the external torque equals the rate of change of angular momentum over time. If the torque equals 0, the total angular momentum is mathematically locked. Back on our swivel chair, the perfectly smooth bearing underneath the seat creates exactly this environment. Because there is zero torque from the ground, the initial angular momentum is entirely trapped inside the spinning student. While that total amount of momentum cannot change, the two physical components that make it up, the body's moment of inertia and its angular velocity, are completely free to fluctuate. The math demands a perfect balance. If one of those variables drops, the other is forced to rise to keep the total sum identical. This brings us to the defining equation for rigid rotational systems. Angular momentum, L, equals the moment of inertia, I, multiplied by the angular velocity, omega. Imagine a child on a frictionless turntable, spinning with arms outstretched at 40 revolutions per minute. The child folds their arms tight, reducing their moment of inertia to 2/5 its original value. Since angular momentum remains constant, speed scales up by the inverse ratio. That 40 revolutions instantly jumps to 100. That is a 250% increase in rotational speed. It is a forced mathematical outcome dictated entirely by the conservation law. This raises one final question. As the rotational speed increases, the total kinetic energy of the rotating body also increases. So where does that extra energy come from if the system is closed? The answer lies inside the person spinning. To pull their arms in, they have to physically fight against the outward push of centrifugal force. They are performing internal work, burning their own chemical energy to fuel that massive spike in rotational speed. We see this energy conversion constantly in high-stakes athletics. A diver in freefall pulls into a tight pike position, minimizing their moment of inertia to squeeze out rapid rotations before hitting the water. Conversely, look at the precise control of a ballerina. By extending her limbs outward, she purposefully increases her moment of inertia. This distributes her mass further from her center, allowing her to gracefully break her own rotational velocity. When the world stops pushing you, your physical shape dictates your speed. The conservation of angular momentum regulates everything from a spinning student in a classroom to the orbits of entire planets. It is the invisible, unbreakable balance governing every rotating body in our universe.